Good morning, everyone, and welcome to today's webinar on the hyperlinks, DDR, DRC, and DC drop analysis. My name is Kung Nguyen. I'm the field application engineer at EDA Direct. Just a few logistics. Please mute your microphone to minimize the background noise and enter any questions you may have in the chat window. This webinar is being recorded, and the link will be available within 24 hours. Please contact Jenna at edadirect.com for a copy of the presentation or a link to the video. We will have about 1 hour today, and I will have a short presentation followed by 3 demos to highlight the capabilities of the tool. Okay, a little bit about EDA Direct. We've been around since 1997, and we have been an authorized distributor for mental graphics EDA tools. We've helped many customers in the high-tech industries with the EDA design tools, as well as product training in some cases. This is just a short list of our main vendors that we sell products and support for. So the agenda today, we'll talk about power integrity analysis. There are 2 areas. One is DC analysis and one is AC. The DC analysis involves with looking at the DC current voltage drop, as well as identifying choking point where current flows. The other part of power integrity analysis, which we will not talk about, is the AC decoupling capacitor. So we do have that capability, but that will be a discussion on a different webinar. The second thing we will talk about is the DRC analysis, and this is electrical DRC. This is not layout DRC. So we will check for things like crosstalk and layout electrical violation, EMI, things like that, and impedance, and even for DDR topologies. So that will be with the Hyperlinks DRC product. And this is something that you can use, and we are proposing this to be part of a product sign-off process. I'll talk more about that later. And lastly, we'll talk about how to analyze DDR subsystems, DDR2 and 3. We do have products that also work for DDR4. But this particular package analyzes things up to DDR3, including the low power version. And follow to that, I'll have demos to show some of these capabilities. So in terms of PCB complexity, well, we see that it is increasing over time. Basically, the form factor has been reduced to smaller and smaller sizes, with the exception of some products, of course. But then the number of layers might be increasing, the stages are getting smaller, the clock speed, the switching rates are getting higher and higher. So therefore, it becomes complicated nowadays. You may have things like PCI Express Gen 3, which is 8 gigabit, 4, which is 16. Let me should we mute some of these attendees here? Okay. All right. So definitely the signal integrity side issues becoming more of a problem. And also, if you have things like FPGAs on your board, you will have to handle and deal with many of the power distribution networks, 5 volt, 3.3, 2.5, 1.8, 1.2, 1.1, 1.0. So many of these rails have to be properly designed in order to have a good signal quality. So overall, we see an increase in complexity and debugging and manufacturing for design going forward. Okay, and so first, let's talk about power integrity and why it is important. A lot of products nowadays are in the categories of wearable, for example. So given the small size, you have less of a power and ground plane structures. You will have less of a decoupling capability, and on top of that, you may have flex rigid design, and this poses a lot of complicated issues in terms of product bring up and reliability in working in the field. And also because of the smaller size factor, you may be constrained to not as many layers in your PCB, and you don't necessarily have a full plane to take advantage of things like EMI shielding and impedance control. So this creates problems in these smaller type of design. Okay. And in general, the kind of PCB design issues that you will encounter basically falls into two areas, with the last being the certification for product, regulation. So we have SI issues for the general interfaces. You want to make sure that you have timing margins. If you have a DDR3 design in a system and you are targeting 800 megahertz, for example, you want to make sure your design has timing margins beyond that speed in case of variance, and also the ability to upgrade, right, to increase the speed. And then because of the smaller design size, the board size, things like that, and traces being routed closer together, there's more inherent crosstalk kind of issues that you need to deal with. So those are for the general interfaces. DDR we talked about, but there are capabilities within the memory subsystem that you should take advantage of, which are things like slew rate derating and write leveling if you have multiple chips that are connected to your controller. So how would I take advantage of those capabilities to help me in having a more robust memory subsystem with lots of timing margins? And then if you have a lot of serial type of channels interfaces, USB 3.1 is now running at 5 gigabits per second, and 3.1 Gen 2 is running at 10 gigabits per second. It's USB. And on the PCI Express, we are looking at Gen 4 at 16 gigabits per second, and they're talking about Gen 5, PCIe Gen 5, which is 32 gigabits per second. So things are getting faster and faster. Board size are getting smaller and smaller, and you will have these kind of issues. And equally important is the power integrity side of things. Do I have enough metals? Do I have enough, the size of the plane is big enough to minimize the voltage drop? Do I have any current choking area, where you neck down your power plane and a lot of current has to go through? So those are considered in the DC analysis of PI. And for AC analysis, we look at the decoupling capacitors. We can't use the recommended guidelines from vendors, 0.1, 0.01 microfarad. You have to pick the proper capacitor at the operating frequencies of your design. So if in one DDR design you're running at 333 megahertz, you need to decouple at that frequency. And the same controller might be used to run things at 800 megahertz. So you need to decouple at that frequency. You cannot use the same decoupling mechanism on both designs. And in addition to that, for power integrity in the AC analysis side, do I have a lot of parasitics? Did I use the correct package? Did I mount those capacitors correctly? Things like via in paths, or do I have extra traces? A lot of those things will have parasitics that can interact with the impedance of the power plane when the product is running. So if you don't make sure that your power distribution network, or PDN, is clean, you may have a lot of signal integrity problems. You may think it is an SI issue, but actually it is an a PI issue. And next is once you've done your SI analysis as well as PI analysis, now you can make sure you pass the EMI regulations. The challenge nowadays is because of the smaller power plane and many power planes within the design. Signal will have to be crossing all these splits and running near the edge of the board, things like that, and it can cause a lot of EMI type of issues. Along with that, the edge rate of the signals from high to low, low to high, excuse me, it's getting smaller and smaller, and these create types of EMI issues. Okay? Now, in terms of providing the solutions to customer to deal with these issues, you can do a lot of analysis in pre-layout. Why is pre-layout analysis important? It is important because you can plan your stack up, you can plan your trace impedance. It allows you to pick and choose your chip vendor package. You know, for example, if you have an FPGA, should I use this low cost version, or should I use a more expensive BGA type of package? Things like that. And also for DDR interfaces, for example, it gives you this ability to test drive different technologies. You know, should I use a by 8 chip, by 16, by 32? Should I use Micron, or should I use Samsung, or whatever? So those are the benefits of doing pre-layout analysis. And once your board is laid out, and before you fabricate the board, this is the last chance to run the analysis again. This is when everything is known. You know, the trace lengths are known, the number of vias are known, the chip vendor have been selected, the connector have been selected, and all of these things. You should run it again. Make sure that your clocks are clean, your resets are clean, EMI type of issues, you know, that you may have. So those are done in the post layout side. And lastly, this relates to one of the products that I'm going to be showing is electrical checking. This is not layout DRC. So let me explain a little bit. In layout DRC, you may set up a constraint that trace A cannot be closer to trace B, you know, let's say 5 mil, right? Cannot be smaller than that. And the tools, almost all the tools nowadays will be able to check those out very easily. However, when they check those traces, they don't know necessarily what kind of drivers are being used, what kind of edge rates are being driven, what kind of frequencies those traces are operating. So it has no idea of those things. And even though you may pass layout DRC, you may fail electrical DRC if you have a trace that's carrying a fast edge. You know, for example, clock would be a good example, but reset is also another one too. You might think that reset is an active, is a static signal. It's not. It might be next to, you know, a strobe line or data line, and these switching activity could be coupling into those reset lines. So that's just one example of DRC. And where do you use electrical DRCs? If you have 1 or 2 design per year, roughly, then you have a lot of time to look at your board. But if you're in the business of producing 5 boards, 10 boards a year, oftentimes or more than 10 boards, you may not have the time to go through and do signal integrity or power integrity analysis for all of these boards. And oftentimes these boards may be designed by external contractor, design house, not in-house. So how do you know the quality of these designs before you actually build them or power up? So if that's a way to quickly go through and check for any electrical violation at the high level, then at least you can identify these problems before committing to those designs. Okay, so those are electrical checking, and if it can be customizable to your own requirement, you know, you may have a spacing requirement and a crosstalk level requirement, and a stack up impedance requirement, a number of vias on the trace requirement that is different from design to design. So if you can fully customize this kind of checking, that'd be good. Okay, so all of these capabilities in terms of doing pre-layout simulation, post-layout simulations, as well as electrical checking is available with Linux. So here is a quick definition of power integrity. Let me see here, some background noise. Okay, I will try to make sure we mute everybody here. Okay, so it should be better now. So yeah, thanks for that note. But if there's any noise, please let me know, and I'll try to mute everyone. So back to the presentation. What is power integrity? The simple definition of power integrity is the ability to have a clean PDN or power distribution network. And the PDN is defined as the path that connects the voltage source to the destination. And the destination can be one device, multiple pins on the device, can be through a connector, and that path may go through the multiple layers of the board, and it can be connectors, and along that path you may have bypass capacitors and things like that. So if the power delivery path is clean to the device, then if you have any problem, it will be, just purely signal integrity related, not PI. Okay. In addition to that, you have some side benefits of from the PDN. For example, given the plane structures and the plane size, it will be able to shield the magnetic radiation coming from the trace switching. You remember the right hand rule? If the current is flowing this way, the magnetic field is flowing around the trace. So those magnetic field will radiate, and the power plane will be able to shield or contain those type of radiation, which can cause crosstalk issue and EMI type of issues. Okay, and if you design the power plane properly, you will be controlling the impedance of the plane across frequencies of operation. So you may have a 3.3 volt, and you have multiple devices connecting to 3.3 volt. Some devices might be running at 100 megahertz. Some devices might be running at 300, 500, 600. So in all of these frequencies, you want the impedance of that 3.3 to be consistent across, not changing, and that can create noise in the planes, and we can see those as ripples. Okay? So those are just a definition of what power integrity analysis will involve. And if you look at a little bit further, you will see that the path does not end at the ball of the device. It also goes inside, and it can go through package routing before reaching the die on the pad, the die on the dot, the path of the die. Okay, so that path is something that can be done and should be done in terms of analysis by the chip vendor. But in this case, we are looking at the PCB level. So we'll be looking at the path from the ball of the device to the rest of the board. Okay? And the question becomes, why is power integrity optimization important? If you look at this example here on the right-hand side, where it shows one implementation of a power plane, you might think that you have the full plane. All these are copper, but that is not the case, because after the routing, there will be vias that will be punched through. It will be fragmented. Okay, and you may have a narrow channel like this, where all of the current have to be passed back and forth between the regulator on the top and the big chip on the bottom here. And through this little segment, right, current density might be very high. And so let's say you have an FPGA design down here, and you're running at 400 megahertz and everything's working fine. And later on, you increase the speed of this FPGA, just having changes internally, nothing outside on the board. And all of a sudden, because it's running faster, it's consuming more current, and it's stressing this path over here. And that might lead to intermittent failures. You might think it's a software issue when you go back to the previous version of the system software, but it's actually a PI issue right here. Okay, so and then when you get this kind of problem, board may be deployed in the field, and through an upgrade, it becomes intermittent. And so it will cost a lot to retrofit those type and mitigate these problems. You have to send it out and swap them, send the field application engineer out to debug the issue. So it is better to contain and design the problem before it gets into the field. And that relates to reliability also too. Okay. So there's a product that we have. It's called the DC drop PE, which is strictly just looking at the DC voltage drop as well as the current density, and that's what I'll be showing today. Pretty easy to use, you can see later on, and it allows you to validate those power rails before going into manufacturing. Very easy to use, no need to be an expert in doing these kind of things. Okay, and then can certainly simulate the traces, the plane shapes. You can do a 3D, 2D view, can identify choke points, and if later on you want more capabilities in this kind of design, you can always add the ability to do the decoupling analysis and the ability to edit this plane structure while you are analyzing without going back to layout. Okay. Hey, well, what if I have a problem? Well, what if I increase the size over here a little bit? What if I add change capacitors and add some of the structure here? Will that help me? And if it does, then I can communicate these changes back to layout. Because there's also routing on the SI side that you have to deal with. So there's a lot of capabilities that you can get to later on once you start doing this kind of thing. Okay, next I want to talk about electrical rule checking, and what is it? This is a rule-based software, and it looks at geometries of traces on your board. By geometries, I'm talking about things like floating islands. I'm talking about traces that are near the vias, okay? Traces that are near the edge of the plane. Traces that are going through the layers and having impedance changes, things like that, okay? That underneath this checking, there is a SPICE engine that runs the simulations and detect these kind of electrical issues and report to you if there's any electrical violation. So this is like doing simulation without you being involved in setting up the simulation and looking at waveforms. You submit the board, you specify the rules, and it goes through and it identify these type of issues. The next step would be to say, oh, really? I have a crosstalk between the reset line and the data line. Well, let me do a simulation on that. I didn't know I have that crosstalk, right? So this is used to identify these problems, and then you can decide how you want to simulate that, okay? So the target audience for this is not for the expert SI engineers. This is for layout people. You just finish your layout. You think you're done. You should be able to run this DRC check before you say yes. It's done. That's one case. The other case is if you have many of these designs per year, 5 to 10, 20. I don't have time to run through all these simulations. Well, let's submit all these boards for checks to see if they pass or if they see any issues. Okay, so it's pretty easy to use. A post-routed PCB is what's needed, and you just go through, set up some of the rules, and just run it. That's it. There's no waveform to look at. There's no analysis. The report's going to be HTML, so that can be shared. Okay, so that's what electrical rule checking is all about. They've changed these number of rules here, but we can look at things like crosstalk issues. If we identify that the traces are pretty close and the edge rate can cause a crosstalk voltage on the victim, Okay, so that's one. Differential impedance, pair phase matching. You may have one length which is longer than the other. One of them may have more vias than the other. As funny as it may sound, I still see this kind of issues in customer design. You have a positive trace that has 3 vias, and then the negative trace has 4. It's kind of weird, but it does happen. I still see those kind of things. And the coupling cap placement, for example, it's best to be close to the chip, but sometimes due to whatever constraints the customer has, or maybe they focused on signal integrity, signal routing, and don't think about power integrity, capacitor placement. And so once it's routed, now you're trying to put down capacitors and you don't have room. And now those capacitors are further away from the chip, which, lessen their ability to function as filters for these rails. So we check for that kind of thing. Another area is things like net crossing a gap. So you may have 2 power plane structure right next to each other, or could be 2 different grounds, and a signal is crossing from one island to the next island, crossing through that open space. And when that happens, if you look at it electrically, the current return path is now longer. There's impedance mismatch. The waveforms are distorted, and by the time it gets to the receiver, the shape of those waveforms are not as good. And the job here is, do I have any nets crossing the gaps? And consistently, I have not found any design that does not have this problem. Some of these signals might be okay. For example, you're driving an LED line, who cares? It can cross over 10 gaps, and I don't care as long as the light blinks. That's okay. But if you have clock nets, reset, strobes, address line, the waveform might be distorted. So do I have these kind of issues? The tool will quickly go through your whole design and tell you how many you have, where you have it, and then let you decide what to do with it. Okay. It is rules-based. Okay, and if on some of the higher version, you can actually write your own rules using the Visual Basic. Basically, just function calls, supplies parameters, and it does geometry checking, and run simulation underneath. Okay, so it is customizable. It is fast, very fast. You will run on a typical board in terms of minutes to go through the whole board. Okay. And then it comes out of the box with default rules and limits for EMI, for PI, and for SI checking. I'll show you that a little bit later. Okay. And then the result reporting, visual reporting, you will see an HTML report that can be sent and shared. The violation will be identified in terms of coordinates and a little graphics to show you exactly where the violations are found. Okay. So that's what DRC is about. So let's go through some of the rules that are involved. So for example, if you were checking for crosstalk coupling, there you can go in and set the maximum couple voltage. What do you want to check for? Is it 25 millivolt, 50 millivolt, or 10 millivolt? And then you want to assume that this is a solid plane and not a solid plane. Do you want to have a list of aggressors? Okay. Sometimes you may know who the aggressors are based on the proximity of those trace routing, but between layers, did you know that the aggressor is actually on the top, on the layer above and the layer below you, not just right beside you like this, right? So it's pretty nice to convenient to have tools like this to crunch through and tell you these things. Also, layout changes. And you, as a design engineer, you might be an FPGA design person. You pick the pin out. You don't know how the routing is done. Conversely, you might be the layout person. You're putting all these traces down, but you don't know how the signals are switching, right? So this kind of merges the two areas together. Differential impedance is another rule. As easy as this may sound, you may have different segments of your transmission line having different impedance values. I just looked at a customer design the other day. They're doing a USB 3.0 Gen 1, which is 5 gigabit, and the traces from the chip going out on the top layer before hitting the via is in the order of 100 ohm, which is not correct. And then transition down into the vias and go into internal layer, and then the impedance becomes 53 ohm. And you got these kind of crazy issues like that. And then when you look at end to end, the waveform is not consistently 90 ohm differential, and your eye will be affected, things like that. So wouldn't it be good to identify those very easy type of issues beforehand, rather than plasterboard and go on the bench and look at things? Yeah. So checking differential impedance, well, while it sounds easy, but you can miss something. Differential pair checking. Well, what do we check here? We check for via separation. Is it too far? Do we have an inconsistent number of vias on the positive and the negative line? Do we have different lengths between the plus and the minus? Okay. So if I can identify those, it'll be good. I've seen a case where they were routing the speaker wire, right, plus and minus, and I assume that the person who's designing this said, hey, it's audio, so I don't really care. The plus is like 2 inches and the minus is like 1 inch. Well, who cares? It's not PCIe. Well, that might be practically true, but why do that? Why not make them the same? And if this was to be high fidelity speaker, that difference in trace length might cause a phase shift in the audio at the end. So just a simple example. I mean, in real life, the difference might be a lot smaller, but things like that should be checked and should be consistent, and those are good design practice. And that relates to this next rule, which is differential pair phase matching. Okay, you can have basically check for the phase, the length, the differences, the impedance, the width, and all these things. Edge rates, okay. Not all signals are switching the same way. Things that are driven from an FPGA is different from things that are driven from the processor. So due to different process technologies that will use different packages, different slew rates, you want to see if these will be faster than what you expected or slower than what you expected. Impedance, okay. Some of these rules might overlap with the layout rule, but the idea behind this is we actually run simulation, and we can check for the tolerance, and things like via structure can actually affect the impedance from end to end. Other things like stubs, you may not be aware of this, but in many designs in the past, people add test point structures into traces, or have stubs going on like this. Some design may use resistor multiplexing. For example, what I mean is, for example, one source, if you're running the board in this mode, then you populate this resistor, and it takes that path. And for a different design, you populate another resistor, and you depopulate the last resistor, and then the signal goes through that path. So they're using this like a must-through resistor. And while that works on paper, in real life, when you are not populating the other components, those are stubs. And if those are clock line, you will get reflection, you will get impedance, all things like that. You don't do that nowadays on fast edges. So it's not about frequency, it's about the fast edge. You may have a 10 megahertz signal, but if it's running, the edge rate really fast, it can be more problematic than a 300 megahertz signal, which has a slower slew rate. Okay. and these stubs actually can hurt you. Uh, and another design I've seen where it's a clock, for example, they have both series and parallel termination, and they pick one or the other. One is to work on the bench and just leave the board as is. Well, guess what? Now those stubs are there, and those cause reflection. Distort the waveform. You don't do that. You don't have the space to do that anymore, and you can't just go out and solder and unsolder components like this. Okay, so stuff. Many VS, as simple as this may sound, it actually is an issue. I've seen design of a customer where they have an address bus, right, for a DDR subsystem, and usually you have like 12 to 16 address lines, and in that particular case, all 10 of the address lines have 4 vias, and 1 or 2 have 6. And why did that happen? Well, they were routing and they hit a bottleneck, can't route anymore, so they jump off into the power plane or the ground, route over the congested area, and then come back down. That added some vias into the address line. Well, the constraint might be, hey, I'm still keeping the length of the address bit to be within 2 inches or 1 inches. I'm keeping the length. So why does that matter? Well, it does, because every via structure that the signal has to go through create discontinuity, create crosstalk issue, reflections, all that thing. So checking the number of via is important. You'll be surprised if you go back and check the number of vias on your clock line, your main clock. You will see easily 6, 8, 10 vias on the clock, and that's not good either. Well, why did I do that? Well, the clock has to go to many places. Okay, but did you know the effects of these vias on your clock? Well, I don't know until I go to the bench. That's where simulation comes in. But this is even before simulation. Do I have that problem? And if I do, is this a critical signal? Then let's not do that. So fix it before you even simulate. T-fork topology. Right? Sometimes you have this structure where you let me see, where you have to match trace length in a T way. Here, somebody is, hold on. Okay, there we go. There. All right. So you can specify these kind of length requirements, and the tool can quickly check these for you. It's very easy for the tool to go through things like this. It's just geometries and length calculation. Very easy to do that. Okay. The coupling cap placement we talked about, it should be closer to the power pin, not further away. You may have metal islands, okay, and these metal islands are not necessarily bad. Sometimes you may have a ground path underneath some component, and the intention is to be a heat sink. Sometimes this component gets hot, and just put a ground thing right underneath, and it's used as heat sink, nothing else, and that's fine. But did you know also that being a metal piece, it's gonna act like a little antenna? It will radiate, it will couple signals from signals nearby into this, and then act as a path to couple those noise into the next signal. So something might be toggling on the right-hand side, and a victim might be on the left-hand side. Well, this guy will act like a messenger to bring those across. Now, the level might be very low, okay? I'm not trying to scare you or anything like that, but over time and a lot of things happen, it might be bad. So that's why when you have an island like that, you want to have a via and tie that to ground or VCC, not leave them floating. Okay. And then in a few designs I've seen where there was a mistake in the layout. They were having different cutout of VCC and forgot to connect one of the islands back to the rail, so it was just purely floating. Okay. Net crossing gap, we talked about that. You can define, the minimum allowable cross length you can define, it might be passing through an opening in a plane like this, and you may be able to define what is okay, what is not okay. Nowadays, a lot of design have this crossing gap in the design, but many times it's okay, but a few times it's not. And if you have to cross, make sure you cross very quickly and you don't go out to an open area and run some long route and then come back and things like that. That's not good from an EMI standpoint. Okay, and then in terms of electrical sign off, you can add this as part of your sign off process, and you may have requirements. Let's see, one something. Okay, I see. Okay, so how can I incorporate this as a sign off process? You go through your normal sign off procedure where people will say yes, design is done, schematic is checked, layout is checked, and now you can add this in that path and say I also check electrical DRC, eDRC. We don't have any of these net crossing gaps. We don't have crosstalk violation. We don't have many vias. We don't have these different, length in impedance matching, things like that. Capacitors placements are good. We haven't done the simulation, but at least the capacitor placements are good. We don't have stubs in our design. Those are ran one time, submitted as one report, and become part of your sign-off process. So by the time when you get into manufacturing, design quality is a lot better. Okay, and hopefully you will have minimum EMI type of issue at the end. Okay, so make this electrical DRC sign part of your sign-off process. All right, so next let's talk about DDRx. Let me see here. There is, okay, some question here. Whoever has surprise eye on the background, please mute. Okay. Yes. Thank you, everyone. Please make sure you mute your microphone to minimize the background noise for everyone else. Okay. So DDRx, why is X increasing? We are talking about DDR, DDR2, DDR3, and now DDR4, and there's low power version, so LPDDR, LPDDR2, 3, and 4. So the clock speed increases. Okay, this one does not have DDR4, but that's okay. We know it runs at 24 mega transfer per second. So clock speed increase to give you more bandwidth. Okay, that is a demand. Memory subsystem is always a bottleneck in terms of bandwidth. Okay, so this one just highlights some of the main differences between these technologies. Okay, so DDR you see max out at about 400 megabits per second. DDR2 runs at 400 megahertz or 800 megabits per second. DDR3 you're running more than that nowadays. Okay, so clock speed increase, data rate increases. Second thing, in terms of DIMMs, okay, or loading on these memory subsystem, when you're running things at lower speed, you can support more load. When you're running things at higher and higher speed, you can support less load. So for example, if you're running DDR3 at 1600 megabits per second or 800 megahertz, and if you're using a DIMM, likely you'll be able to drive just one-sided, slot, not two, because of the loading, capacitive loading. And then in terms of signaling, we went down from 2 volt to 1.8 volt to 1.5 volt, and then to 1.2 volt for DDR4. And because of all these impedance and switching and all these things, they added this on-die termination capability. That opens up a slew of issues, problems, things that actually challenges, right? So there are many ODT settings that I can set. Which one is the best for me? Number one. Number two, I used to do my trace impedance at 50 ohm. Is that the optimum trace impedance, or should it be 42, 43 ohm? Why do I need to choose that? Because of the ODTs. So now when you have this flexibilities in terms of selections, it also creates challenges in which combination is the best for my design, which is a smaller one, compared to his design. There's a bigger size, all that kind of thing. And then with DDR, there are things like flyby architecture, where you have signals that are daisy chained, for example, address lines, and you have signals that are point to point, right? Source synchronous. For example, data, DQS, and the data, right? The data bit. Controller is driving the address based on the clock, but these address lines are connected in series. So if you have, for example, 8 chips, and if the controller is driving one address line, okay, it has to drive this in a serial fashion. On the DIMM, on the board, you might choose to use a T topology to distribute 4 and 4, So which one's better for me? And then the termination is at the end. So, things get difficult pretty quickly. Which way is best for me? So simulation will tell you how far you can push the technology against guidelines. Okay. Many people just follow guidelines blindly without thinking or knowing how much margin they have. By running simulation, you can actually look at both guidelines and margin that you have. And sometimes if you have a lot of margin, you don't need to follow guidelines. Sometimes you follow guideline, it creates problem in your margin. Let's say you're doing this as a T routing. One address line takes one path to 4 chip and takes another path to the other 4, right? Hey, I'm keeping the length to be the same. Well, that creates signal quality type issue, and you can look and detect those in simulation to see if it's okay or not. And then for DDR structure, sometimes they have this thing called training. And training is basically from the controller sending bits, doing reads and writes to the memory subsystem to determine the delays and to position the strobes. Okay. And once they figure that one out, then those values are programmed into the controller. That's good, but that does not mean that your layout, you can be sloppy in your layout. Hey, let the controller take care of this for the variation. No, you assume that this auto calibration does not exist, and then you design your layout to the best that you can. Once you're done with that, now all of these calibration, will help you out. Okay, so for that type of DDR analysis, we have this package called DDRC, and that allows you to run DDR2, 3, up to 3. And if you have a need to run DDR4, we have a path to do that. This is a smaller package that allows you to do post layout timing analysis. Okay, so in the full package, you can do both pre-layout and post-layout, but this is lower cost version. It allows you to do post-layout. And this would fit many customers' requirements. Sometimes they have design done outside, design done by a contractor, whatever. They buy this module from somebody else. And they hook it up to their system, and they just interested in doing post-layout, and that's fine. When we run the analysis, we will generate an HTML report, and if there's any failure, we'll show that. And these failures are linked to waveform, so you can click on the failure, and the waveform will come up and show you where the measurement took place and how much margin that you have. And then if you want to do a simulation in the full package, you can extract those nets from layout. And then do eye diagram and look at changing things, okay? But even at the post layout level, you can check for things like overshoot, undershoot, ringing, and it's not just those simple parameters. We also check these values against JEDEC specification. You may or may not be aware of this, but in the DDR subsystem, it's not just setup and hold, and overshoot and undershoot. It's not just that. JEDEC defines additional parameters that you have to meet if you want to say I am JEDEC compatible. So things like the symmetry of your differential pair, your clock signal, for example, it has a positive and a negative signal. The strobe has a positive and negative signal. These do not necessarily transition and cross over at the same time. These might be skewed because of the routing between the plus minus, because you have different vias, number of vias on the plus minus. There's a skew, and JEDEC defines the maximum skew, for example, and those will be automated and checked for you. Another point about overshoot and undershoot, JEDEC allows you to overshoot or undershoot, but within a certain time. You can't overshoot forever. Uh, so if you don't have these automation checking done on your subsystem, and let's say your subsystem is, 32 data lines, 16 address lines, bunch of control lines. So you're looking at 60, 70, 80 signals to check. If you don't have the automation, you will have to check each signal. You have to measure manually. You have to calculate. You have to bring all these JEDEC limits out and compare. It's a pain, and that's where automation help you, and computer can go through these kind of scenarios very quickly for you. Okay, relieve you from doing all these calculation and just let you focus on the failure. Okay, that's the advantage of automation. Maybe a couple of things here is design consideration, just a few. Avoid crossing splits in the routing. And for power supply, use precision resistor for reference voltages, or better, use an active voltage regulator to generate your 0.75 or 0.6 or whatever. And then make use of the on-die termination. Okay, and sometimes in your design, even though the product is working, you may have a criteria to save power. For example, it might be a portable device, it might be an IoT device, it might be a Bluetooth headphone, whatever the case might be. If you need to save power, you need to look at the signaling. Because sometimes your address line might be ringing, and those ringing, even though it's within the voltage limits for highs and lows, those ringing will consume active power. And by running simulation and see those and terminate those properly, you actually save power. Okay, and sometimes even people cheat, right? At 3.3, but I'm actually going to lower that supply voltage to save power more. How much can you lower? How much margin you have? Okay, so even though things are working, it doesn't mean you can't optimize it further. Okay, so anyway, if you are in an environment where you can do both schematic layout and simulation, SIPI as well as thermal, something we didn't talk about today, but it is also important. And electrical DRC checking, if you're within this environment, then it's really easy to look at things, pass parameters back and forth. Okay, one central place, simple single debug environment, and you minimize all these finger pointing, different vendor tools, and single support source. Okay. All right. So the benefits of having this checking is to validate and optimize your power distribution network. Okay. Make sure you have enough copper. Identify choking points in your routing. You can do the electrical design rule checking before sign off. And then you validate your DDR timing, right? My 800 megahertz DDR now has margin before having a board. And in terms of bringing the tool or the board files into these tools, we can always go through ODB++, which is a standard. Okay. And the demo design that I'm going to be using today is going to be the BeagleBone black board, and this is basically a TI ARM-based processor. It has DDR3, NAND flash, Ethernet, USB, HDMI, micro SD. So it's pretty decent, small enough that we can run through things easily, and it's representative enough of things out there, and we can see. Okay, so that is the presentation, and I would advise you to go to our website, edadirect.com, to check for upcoming seminar, workshop, training, as well as watch videos, product demos of videos of some of our products. Okay. All right, let me just now run the tool and demos. Okay, over here. So let's just bring this one up. It's pretty easy. Yeah, let's just up. Okay, fine. I'll just do that. Stop it over here. Easier. Okay. So we'll just select the particular package. So I'm only running things within the capability of those packages. So first we want to run DC drop, and let's just run this one. Okay. And nope. So this is the BeagleBone board, and first thing that you should do always before you click anything in terms of analyzing this is to check the stack up. Okay, make sure that these values are what you expected. The dielectric values are what you expected. 4.3 FR4, solder mass or not, layers, thickness of the board, all that stuff. Okay, you can always customize and change things in here and move things around if you want. Okay, so next thing we do is we define the power supply, okay, for the nets, and the one that we are interested in is called VDD MPU, which is defined as 0.8 volts. So you go through, define this one time, only one time, okay, on all the rails, or just the rail that you're interested in running the analysis on. That's all you do. Then you go to here and say run DC drop simulation. And you can quickly go through the power plane structure and see what they look like here. Okay. And we will be using this net. Okay. So this is basically the VDD supply voltage to the CPU, right? 0.8 volt. The source is down here on the lower left, and this destination is up here. Now, before you do any simulation, you need to look at this and see if it makes sense, right? If the source is on the lower left and the upper right is the destination, and if I'm generating a voltage from the lower left to drive to the upper right, you don't want to have narrow traces like this. That create that's a resistor. You want bigger planes on this side to minimize voltage drop. So in this design, they didn't do it properly from a topology standpoint. They're sneaking in with a little trace and then expand it out. Well, guess what? By the time the voltage gets to here, through whatever current amount that it takes, the voltage already drop. And now having a big plane will distribute that lower voltage to the chip, which is not as good as having the bigger plane on the left and a smaller trace on the right. Okay, anyway, so that's looking at it. Then you go in and you assign the source of the VDD MPU is coming out from U2, which is an active regulator. So I'm going to select that pin and I'm going to say, hey, that is going to generate 0.8 volt. I'm going to model that with a simple regulator definition here, and a little bit of a resistor and an inductor, okay? And what that does is it's going to set this point to be 0.8 volt, and it can generate infinite current, okay? The objective here is not to design the regulator. The objective is to see from this point onward, based on the loading of the device, how much voltage drop do I have. So in this case, we have one device with these power pin connecting to that, and we can say assign, and you can, in this case, we are, using 0.5 amp per pin, or you can do a whole group, whatever. So that's the case, and everything is referenced to the digital ground net. Okay, so we just define the source, the load, the reference, and that's it. And over here, we'll create an HTML report. We'll set up some limits. Is the maximum voltage drop more than 50 millivolt? Is the current density higher than 10 milliamp per mil square? Do I have any vias that carry more than 1 amp of current, right? Any of these fields you can change. And then you write all this report out and basically just say simulate. There was a question from the audience. Can we get a copy of the presentation? The answer is yes. And please send email to Jenna. I put that down in the text window in the beginning. So in the chat window in the beginning. All right, so let's look at this HTML report. It's reporting that I have a maximum voltage drop failure, and the maximum value was 53. I set it to 50, and I saw 53. Oh, where is that? It's at this pin right here, U5 pin J13. I also have a problem with current density. It also failed. I set my limit to be 10 milliamp per mil square, and I'm seeing 168. Where is that? Is at this location right here on layer 3. And I set my maximum via current to be 1 amp. That's a failure. That's a location where the current was 2.3 amp, and it's right here, okay? And then there's a listing of, things in here which you can go through, blah, blah, blah. That's the report, but we're going to look at the graphics now. So here we're looking at the voltage drop display, and here on the left-hand side is the scale, okay? The highest voltage and the lowest voltage. So the highest voltage come from where so looking at this is more in line with, what you're seeing earlier, right? So the source is down here, and the destination's up here. And you can see we are setting a threshold plane of 760 millivolts, which is 5% down from 0.8. So what we're saying is there any part in my power plane that exceeds 5% margin? And the answer is yes. I have a little section right here, and that's that's because I have a narrow trace here and a bigger plane here. You should have a bigger plane here and a narrow trace there. So you can quickly identify that yes, okay. Now let me go around and measure things. I can put on the cursor and I can say, okay, here's 0.794, and it's dropping down, and lower. If you display this in 3D, you will see, yeah, that's some area that is pretty high. Now it's kind of hard to see here. Let's change that to 2-dimension, 2D display, and I can zoom into an area where I can see high current flowing. Okay? Now, despite what you might be thinking, hey, I have a full plane here, I shouldn't have problem. Well, yes, you do have problem right here. And this is because the way current flow is it's going to pick the path of least resistance. So the distance from here to here is shorter than the current having to flow around through here. So therefore, everybody's cramming into this area right here. And if I can just kind of change the scale, I can see that there's a high amount of current flowing through this narrow area, this as well as here, okay? So in this design, I have both issue. I have both current voltage drop as well as current density. So how do I fix this? Well, I can edit the section and add a little copper path to minimize this current. Okay, no, that's why. Okay, so now you should be. Now you should see, right?
Yeah.
Something's coming.
Now
Okay, great.
it's
Thank
right.
you. So this is the DRC tool. I apologize for that. There was some net glitch. Maybe everybody's trading Netflix or Facebook today. I don't know. This is the DRC tool, and this is what it looks like. And let me just bring in a design right here and bring it in. And this is what it looks like. Slightly different, but it's the same board. So what we're doing is we're going to look at the rules here, and we have these EMI, crosstalk, whatever, SI in here. So for example, we look at let me see here, net near plane edge. Okay. So what is this rule? This rule said, do I have any net near the edge of the board? What does the edge mean? It doesn't always mean the size, the left, right, top, bottom. It doesn't mean necessarily just that. You may have a cutout inside your design, and there's a trace running near that area. That is an edge by definition. And the magnetic field can and will escape from the trace outward, as well as magnetic field can be coming from outside into the trace. So you want to avoid this situation. You want to define the minimum run length as well as the minimum distance from the edge, things like that. Okay, so that's a rule. And let's just run it, okay, just to show you. So I'm enabling all these rules, and I'm going to say execute them all. And so it's going through. I already ran it once, that's why you see some red and some green. I'll just rerun the whole thing again, just to show you how quickly it is to run through all of these rules on a small design like this. Even on bigger design, it will be running in minutes, not hours, okay? So the idea is really to go through these parameters in each of the rules, set it up to what you want. For example, maximum number of vias. Okay, how many vias do I allow to be maximum in my design? Is it 2? Is it 4? Is it 8? Is it 10? So set a number, and it goes through and it finds. So for example, you say, I don't want anything more than 4 vias. Just put number 4 down, run the rule. It goes through all your signals and check everything to see if any signal has more than 4 vias. All right, as you can see, it's pretty fast. What I have here is a Intel i7 quad-core CPU. Here, I'll show you my configuration. Not trying to show off, but here's a i7, quad-core, 16 gig of memory, Windows 10, and dual graphic card with SSD. That's it. Pretty simple, typical. So it runs through all of these within 1 minute and 22 seconds, and it finds all of these problems. So let's look at a few of these. So net crossing gap is easy to see. Spreadsheet. Okay, so we have okay, spreadsheet violation. How many violations do we have? We have 195 violations of net crossing splits. Even on this simple small board, what does one look like? Here's one. See, you can see it's crossing this gap. You can see the next one, crossing that gap, crossing the split, crossing this, crossing that. And it tells you where it is. It tells you, you can zoom out. Let me see, zoom out here. See, I mean, it's kind of, by the way, this board works in real life, but it is work for people who want to play around with things. This is not used to control, your pacemaker or missiles, or has to work in Alaska or in the Galapagos Island, right? So, but people will say, hey, that's a reference design. It seems to work. Let me just copy as is, and you propagate all these errors along the way, and you don't even know that. That's crossing split. Very easy to see. Near plane edge. Do I have any violation? Yes, I do. I have 7 violations. What does it look like? Here. Well, look at that. What is that? See, here is not crossing gap, but it's near a mounting hole opening. Did you know that, right? That you have that problem. Now, this might be a problem or not a problem, up to you, but we're telling you that in your design, you have these kind of things near the connector. It's near an opening. It's near the edge. Uh, Here's another one near the edge, right? Lots of these things. And again, could be an issue, could not be an issue. You decide. We just tell you we found them. IO no, let's see, that's a crosstalk coupling pass, but IO coupling. IO coupling, what is that rule? That rule says I have two signals that are running near each other with some separation distance and with some length along the way. Okay, so I set these limits, and the tools just go through and say, hey, I have any signals that violate this. And so I have, how many here? 14 violations. And let's look at one, there's some signals that are running next to each other for a long time. That's bad. And believe it or not, I actually help customers find an issue with they have a reset line that goes all over the place on the board, and in some places they have a data line that's switching, and some places running near the clock. So you just need one or two sections like that inject noise onto the reset line, and if it's big enough of an issue, you will get into intermittent system reset problem, which is very difficult to debug, but in this case, it's very easy to fix. Okay, so that's just that. Differential vias. Let me see, two large length difference. Right here's the routing differential line, and it's not obvious by looking at this, but there is a difference in the plus and the minus length. So things like this are very quick, easy, even many vias, right? So that's DRC, okay? And we can generate an HTML report to look at all of these things. I won't go through that because of time. So let's do the last demo, which is the DDR. And I need to make sure I'm selecting the right package here, DRP. Done. Okay, so let's run this quick. And in this design, it is an ARM core, DDR batch simulation. Okay, and we go through here, and I'm going to load a setup file just to minimize the time here. And that setup file says I am running this as DDR3. Okay, I'm using 1.5 volt, or I can choose different low power version, and I'm running this at 800 mega transfer, which is 400 megahertz, or I can change to different rates. Okay, and the controller is U5 from my design, and then the memory chip is U12. Okay, U12 here. So one controller, one memory chip. This is a low cost board. You may have 4, 5, 6 memory chips. Is okay. Here it said I have the IBIS file for my controller, and I have the IBIS file for my Micron chip. These you get from the vendor. Okay? And then I'm going to do both read and write cycles, and there are more parameters in here for DDR checking, timing checking. And if you deal with this, you will know what these are. I'm not going to explain all this. And then let me see here. Next, we're going to be analyzing everything here, all the signals, all the address lines, all the data lines, all the control lines, or I can selectively just run a few, okay? In this case, I'm going to run everything. Then here is the page where you select and set the ODT values. This is probably the most difficult part in analyzing a DDR structure, because you have to go in and kind of select what are the ODT settings that are available from the vendor for you to use. Now, the problem is that you have to know what value to use, because you have to tell software guys, tell firmware people to program these values, these settings in the memory controller, in the memory chip, as the system is coming up. It does go through this initialization process where the controller comes in and program things. Software does that. You have to tell software what to set to. Okay, so this is not just an academic exercise. And also going through this different ODT settings allows you to plan your trace impedance on your board. Okay, and these values are changeable for both the controller as well as the memory chip. So imagine if you have to debug this memory subsystem on the bench. You want to vary all these values on the bench. It's going to be very difficult because you need software support to go in and help you change this, reboot the system, blah, blah, blah. Painful. Here in simulation, just a few clicks and you can see the result. Okay, let's go skip through some of this. And we can also look at the effects of crosstalk if you want, and be able to do a little bit of a power integrity effect in this signal integrity simulation. I can explain a lot more later, but let's just do all three corners here: fast, strong, typical. I usually advise customer to just do typical. The reason for that is when you do the analysis in typical, you can actually see both sides. You can see margin for both sides. And if you tune it to pass with lots of margin in the typical case, likely you already taken care of fast and slow. Okay, but in this case, I'm going to turn them all on. And this is what I mean in terms of JEDEC checking. Right? So JEDEC defined a standard for DDR2, DDR3, DDR4. All these measurement values, these parameters, these terms, VIX, minimum VIH, overshoot area, undershoot area, and a bunch more things, particularly for each different memory interfaces. And the tool will automatically grab these numbers, these limits, measure the signal, compare against these JEDEC settings, and tell you if it pass or fail. Now think about doing it that way versus doing things manually, where you simulate the signal, see the waveform, instrument your cursor, take down the measurement, add, subtract, multiply, whatever, and then compare that to JEDEC. Painful, right? Automation, let the tool do it. Okay, so next, some warning here. It's okay, no problem. Just say save that setup file and just run it. Okay. So what we're doing here is we're doing both reads and writes on all of the memory system signals, all the data line, all the address line, RAS, CAS, write enable, chip select ODTs. We're changing ODT settings also. There was one more area which I didn't show you guys, but you can actually sweep through the ODT settings. Remember those big selections, of the chip, and then smaller selection for the memory controller. Those create a lot of combinations. So you can actually set up the tool to go through those combinatorially, like one of this and two and that, go through all permutation. And then at the end, you will just look at the result and pick the one that works best for you. Okay, let me see here. Open up chat window. Oh, there's some question. Okay, there was some no, some yes from Jinny Young. Okay, I don't know what that was. Okay, so let me type in the window again the contact information. Okay, so please contact Jenna if you would like to have a copy of the presentation and a link to the video. We'll wait here a little bit, let this simulation finish, and then I'll show you quickly and we'll be done. So one thing to note is this is a post layout only. Okay, so wait, how come we have a report right here? What is this? Oh, that's from the old one. Okay, what is this? Control panel. Okay. So this is a post layout only. What that means is, yeah, post layout, can't do pre-layout. In real life, we would recommend you to do pre-layout also. Again, it's not because you want everything, but the earlier you catch design issue, the lesser a pain that you will have to go through. Okay, and it costs you more. That's a 10x factor when you're jumping from pre to post. And if you don't do simulation in post and you go through manufacturing and go into the field, that's another 10x factor if something fail in the field. So it is advisable to check things out in pre-layout. It also allows you to explore technology. You know, today I have this design, I'm using 1 micron chip, and this is the performance I'm getting. But what if I use 2 micron chip? What if I don't like TI? I want to use some Cavium processor. I want to use Xilinx on this. Can I do that? Can I put it in? You know, those are exploration phase that you can go through in terms of simulation and help you to define your next architecture, help you to select your connector, help you to select your fab house because you are checking the stack up. Okay, you're playing around with stack up values, and you can talk to your fab house and say, hey, can you guys do this stack up or that stack up? If the answer is yes, great. If the answer is no, well, they can't do what you want. So a lot of benefits for doing pre-layout, not just post-layout. Once everything is done, you can't really change anything once it's done. So it completed. Probably take like 2-3 minutes here. I don't know. So we have data rights, and you can see it's all passing. And you can see also, even though when it's passing, you should look at the margin. Here it said I have 152 setup picosecond, but my hold time is a lot. So maybe the trace is longer than it should be. I might be able to shorten those traces and improve the setup and take away some of the whole margin. So you can see, oh, there's a failure here on D2. What is the failure? It's failing this VIH value. And if you click on that failure, waveform comes up, and you know, there, that's where the measurement was done. Okay, no, let's look at the setup and hold of just a typical one, right? Here's the setup. So all of these values are linked to waveforms, and you can see, you know, you can also move and add cursor and do things like that. Okay, so that's the waveform on the right. And let's look at the read. So now you know that D2 and D3 has some issue, but everybody else is passing. So you focus on D2 and D3. And then on the read side, there's some failure here. There's a hold time violation with D8. So even though D8 works on writes, it failed on read, okay, with this whole margin. And click on that, we'll see where the failure is, right, where the measurement were, move the cursor around, whatever. Now on this, and then let's look at the address lines. Okay, was everything done here? Well, I got some violation with overshoot, right, on address CAS. CAS has overshoot of -23. Let's click that. Okay, that's an overshoot. So maybe termination is not quite correct on the CAS line. That's why they have series resistor on RAS, CAS, and write enable to mitigate these problems like this. Now you may not be able to do that in your design, but at least we'll show you there was an issue on this. And there's a whole time violation on A1. Okay, differential net, what do we have? Symmetry, overshoot area, everything's passing. Even though it's passing, please look at the margin to see if it's symmetric. Skew, do we have any problem in skew between clock and DQS? So that's basically it, right? So we and the results are stored. This is a batch simulation, so all the waveforms are stored. You can always go back and look at it. And if you have a bigger version, you now can look at a particular failure, extract that net out into schematic, and then change and do what if I change the length, what if I do this and that. Okay, question from the audience. Will the program give recommendation for routing? No, we are an audit person. We will tell you if it pass or fail. How you do the fix is up to you. You know, let's pick a simple example. You have a hold time violation. Okay, so how do you fix a hold time violation? One way is to increase the trace length. How much to increase the trace length? I don't know. It's up to you. How much margin do you want? Is that the only way to fix hold time? No. You can also change the slew rate. You can also add the resistor. You can also add a capacitor. So these multiple type of solutions, how do we know which one is best for you? You know, based on your time frame, based on your cost criteria, based on your, you know, whatever. So we can't give you recommendation for rerouting. Next question. Can we select only critical nets to check the ERC? Very good question. Excellent question. In fact, let me explain a little bit so you can understand. In simulation analysis, there are two ways to go about this. One is bottom up and one is top down. Bottom up means I have a design, I'm adding these 10 signals that are new, that are really fast, that are, you know, important. So I'm going to analyze those 10 or 20 or 30 or 5 or 2, whatever. Once I finish that, okay, what else should I look at? Okay, maybe I can look at this. Maybe I can look at that. So you go from bottom up to the whole design. The other approach is top down. Top down is what ERC is. So here's my whole board. Just go through everything for me. Okay. But the problem with running top down is you may have lots of errors that are not true. You know, for example, you may have LED signal crossing the gap. Who cares? You know, it's okay. LED line's fine. Resistor pull up, pull down. You know, thing. So you have to filter those kind of things. So that limits your what you can do is you can define a group list. Hey, I just want ERC to check DDR signals only. Only check the signals that begins with DDR underscore asterisk, right? So all the DDR signal, I only want to check with this rule. And then all the Ethernet signal, I want to check with that rule, right? You can define a list and you can tell the tool to just run a subset of that list. So that hopefully answers your question of can we select only critical nets to check in the ERC? Yes, we can. We cannot not just one critical net, we can define a group. Okay, so my apologies for you know, running over time. It always is, and I hope that was useful. And I know I did not show more things in here, but due to the limited time that we have, I just want to expose you to these methodologies. Let us know, please contact us, and we can discuss what you're trying to do, and hopefully we'll have some solution for you, which may be just within these packages or could be outside of this. We can also discuss thermal analysis. We can also discuss analog simulation. We can also discuss FPGA simulation. Okay. With that, thank you very much for attending, and I hope you have a good day. Thanks.